Good morning, dear students. So in today's class, we'll be talking about transistor. Clear applications of diodes. I'll do it after transistor. You see, transistor. It appears to be complicated, but if you listen carefully, it is easy, and you will remember it easily. Understood? So I want your full attention. Now, let's start with transistors. Now here you have to understand the word transistor. How is this formed? Transistor. Now this is formed from transfer of resistor. This is, if you split it, this term is transfer plus resistor. Now transfer plus resistor, they made it as transistor. Here transfer plus resistor doesn't mean that you are taking a resistor and shifting it somewhere. It actually means that the transistor means that uh, transfer of resistance, transfer of current from low resistance region to high resistance region. Transfer of current. Somehow, okay, how we are doing, that's what we need to find. But overall, the output is that we'll be transferring a current from low resistance region to high resistance region. Understood? Low resistance to high resistance. So that's how the name transistor was framed. So you'll understand from this low resistance to high resistance point towards the end of transistors. Okay, when we have finally mastered how a transistor is working, and when you finally try to write, okay, write all the parameters, then you'll understand how it is exactly transferring from low resistance region to high resistance region. Now coming to this transistor is a three-terminal device. Understood? In diode, there were two terminals, but now in case of transistor, we have three terminals. Now coming to these three terminals, so there we had either P and okay, the diode was made up of P and N, right? Now here you have two types of transistors. One is NPN, the other one is PNP. Understood? NPN and PNP. Okay. This is a PNP. This is a NPN. So this you call PNP transistor. This one you call it as NPN transistor. This is PNP transistor. This is NPN transistor. So both these transistors are collectively called as BJTs. BJT, that is nothing but bipolar junction transistor. It is called bipolar junction transistor. Now here, between this P and N, there is one junction. Clear? So I can call this is junction J1. Here between N and P, I have another junction. So this is junction J2. So here also junction J1, this is junction J2. Now, does bipolar junction transistor mean that there are two junctions in the device? You see, in this in a diode, a PN diode, there was a single junction, but now in this particular PNP or NPN, whatever it might be the combination. So here we have two junctions. So do you think that they have named the bipolar junction transistor? It is under semiconductors only. So we have seen about diodes, then we are talking about transistors. Now the reason is that if at all there were two junctions, okay, two junctions, then two junctions, J1 comma J2, then I would have called it as polar bijunction transistor, right? Bi means two. So here, this is bijunction. Bijunction means two junction transistor. Is that right? Suresh, the topic is semiconductors. It's a continuation of diodes. So in that there is a subpart called transistor. If two junctions were there, then I would have called it as polar bijunction transistor, just to indicate that there are two junctions. But here, bipolar is there. But this is not right. They said bipolar junction transistor. Now, bipolar. Polar means what? Charges. Is that right? Polar means what? Charges. Now, he's saying bipolar. Bipolar means two charges. Two charges means two types of charges. Take or participate in conduction. Two types of charges participate in conduction. Understood? What are these two types of charges? Two types of charges means electrons and holes. Electrons and holes are the two types of charges which are taking part in conduction. So in a bipolar junction transistor, okay, just like a diode. So electrons and holes, both of them will take part in conduction. That's the reason why we call it as bipolar junction transistor. Then comes a question: can there be unipolar junction transistor? Then question: yes. So we have something called unipolar junction transistor also. So that is not in our syllabus, but we have certain type of transistors, okay, certain type of design where there will be only single charge, single type. You're correct, Vivek. Vivek says that wires are unipolar junction transistors. You see, okay, I agree with you that the electrons are the only one which are taking part in conduction. But the issue is wire is not a transistor. Understood? Wire is not a transistor. So this is single type of charge. That means electron or hole shall participate in conduction. Yes, electrons and holes will take part in conduction. So that's the name. Now, why I'm stressing on this point means, okay, whenever you go for Viva, they may ask, what do you mean by this bipolar junction transistor? So that's the logic over here. Now coming to this, how is this PNP or NPN model looking? This model looks as if it's like a sandwich, right? It's like a sandwich. So here there's a bread. Between two breads, there is some material placed. Understood? So, in fact, you can call this a sandwich model. Okay, that is called a sandwich model. PNP and NPN. So that is a sandwich model. Now coming to here, the thing is that we need to particularly talk about this. Particularly talk about this transistor. Okay, we have. Let's try to understand it in detail. Let's talk about the parts of this transistor in detail. This is what is called emitter. This region is what is called base. This region is what is called collector. Understood? So emitter, base, collector. Now what's the role of this emitter? Means it will emit charges. Emit means it will supply current into this region. Clear? Then yes, sure. There are unequal cross sections. Now this some part of current will be coming over here. Here, so this is the base terminal. This is the emitter terminal. Base terminal. So current IB will be coming out. So this current C, that is nothing but IC will be coming out. So what will happen is that whether it may be NPN transistor or a PNP transistor, what will happen is that emitter will emit some current. Emitter will emit some current. So that current will come out of base and the collector. Here, so here the names emitter, base, collector. Yeah, we'll talk about it. Why are they of unequal lengths? Just wait for a while. So what's the role of emitter is that it emits, okay, it emits the charges. It emits the charges. Now collector must collect the charges. Is that right? You see, this is supplying charges into it. Let's say if you're talking about holes, as in that this is a PNP transistor. In this PNP transistor, what is this doing is that this is supplying holes into the region. This is supplying holes into the region. So that holes, out of all those holes, so part of these holes will be coming out, and most of the holes will be taken, absorbed by the collector. Okay, these holes will be coming into it. It is they are being collected at the collector terminal. So the role of emitter is to emit the charges. The role of collector is to collect the charges. I hope you understood the naming. So that's a very appropriate name. Emitter will emit the charges. Collector will collect the charges. So base is there in middle. Base is there in middle. Like you see, what is happening over here? Let's talk about the unequal dimensions. Unequal dimensions. Now, usually the base is very thin, very thin. So if this is of 150 mm, the total length is of 150 mm. Understood? The thickness of this base is just 1 mm. That much huge variation it will be there. I don't think 150. Okay, it's not mm. Maybe it's micrometer. Yeah, if this is 150 micrometer, this will be 1 micrometer. So that means the base is very thin. Understood? The base is very thin, but I cannot, if I draw it in this exact proportionate ratio, then I cannot represent all these terms. So that's why I put the base a little fat, but in reality it will be very thin. Now what's the role of emitter? You see, emitter emits charges and collector collects it. And collector collects it. So in this case, if the collector is collecting it, what we can say, that means this implies, okay, from here one conclusion I can draw. One conclusion I can draw. What must be the conclusion? Doping of emitter must be greater than that of collector. Why? Because if the doping of emitter is greater than collector, then only due to due to concentration difference, concentration difference, diffusion takes place. Is that right? Diffusion takes place. So first thing we have understood that coming to doping, first thing we have understood that coming to doping, what must happen? The emitter and collector, the emitter, whichever is emitting the electrons, must be highly doped. And coming to that of collector, it must be low. So shall I write here that here that is doping? If I am trying to write about the doping, so if I write this emitter, base, collector. So doping of emitter must be high. Doping of collector must be moderate. Now, why moderate? We wanted the diffusion to take place. So the greater will be the diffusion when greater is the doping difference in the doping levels. So the collector must be low, right? It must be a low doping case. But why are we writing moderate? Because the base is purposefully maintained low doping. The base is maintained. Okay, the base is purposefully maintained. Okay, that means the base is purposefully doped as low as possible. The base is purposefully doped as low as possible. Now, what's the reason for low doping is that, you see, charges will be coming over here. It's an N region. N region means what? There will be some electrons inside this. So if the number of electrons are more, if this holds in the process of crossing this base, okay, what this holds they try to do, that try to cross the electrons, a base region, and they reach the collector region. So in that process, if they come in contact with the electrons, what will happen? No, intrinsic base we cannot use. Yes, they annihilate, they neutralize. Neutralize means they just vanish. Understood? Previously, if electron jumps out of the atom, that form the electron hole pair. Now the electron and hole combine, so the charges will not be present. We say annihilate each other. Okay, they'll destroy each other. In reality, they're not destroying, but they're not on the screen now. They're just neutralized. So in that process, that means here, what is your main aim? Your main aim is to send charges from emitter to collector. Your main aim is to send charges from emitter to collector. But in that process, if most of the charges are being killed in the base, would it be a will it be a good what design? No, right? That means the charges, okay, whatever charges you're sending, they must reach here. Whatever charges you are sending, they must reach here. So charges must not destroy each other. That means this holes will get destroyed when they come in contact with electrons. So the number of electrons in the base region must be as low as possible. Understood? So here I'll mention. Note, to prevent uh, no, how will ions form? They're purposefully doped, right? Here there are donor atoms which are excess in electrons. Here it is a hole. Hole means vacancy is there. So when electron goes and comes in contact with the hole, so that means electron is joining a atom where there is a vacancy. So it will not form an ion. It will neutralize. To prevent combination of electrons and holes. The doping of base is maintained as low as possible. Understood. To prevent combination of, not combination, recombination of electron holes. The doping of base is maintained as low as possible. Is that right? So did you understand the doping? Now, how I usually remember this is, okay, that may look silly, but how I remember it is that I remember this as large, medium, small. Large, small, medium. This is how I remember. So because emitter must be emitting, so its doping must be large. The collector is medium, and I know the reason that combination must not take place. I remember it as small, but actually high, low, moderate are the proper terms for doping levels. I remember it as large, medium, and small. Now let's come to the size. Width. Here, let's come to the size. You see, emitter is emitting the charges, but who must collect it? Collector must collect it. So that means there must be enough room in collector for the incoming charges. Is that right? Collector is collecting means that means collector must give shelter for all those additional incoming charges. You see, since collector has to accommodate the charges, the incoming charges, the size of collector must be large. Is that right? That means its width must be large. Large means compared to emitter. Understood? You see, emitter is emitting the charges, but the thing is that all those charges are leaving, right? So when they are leaving, so even if the emitter is of moderate size, it is not going to make any difference. It's not going to make any difference. So emitter must be the size, coming to the size or length, because the cross-sectional area is fixed. Size or length, what we can say, this is emitter, base, this is collector. So in this case, this must be of large size. This one is of moderate. Here also the size of the base is, or the length is small. Now here how I remember it is, collector must be large, the size of the collector must be large, L. This is medium, M. Small, S. Large, medium, small. Is that okay? Here, okay, I'll tell you the reason why the base is small. But here, the only the thing is that doping. If you can see in both the cases, in coming to the size as well as doping, the base is small only, but the emitter is large here and the collector is small. Then they are interchanging. This emitter becomes medium and the collector becomes large. Understood? So large, small, medium, medium, small, large. So in between the base is there, but the collector and emitter, they're just exchanging. Now let's see why the base has to be small. Why the base has to be small. For that, let me draw the diagram for the base. Okay, you see. Mm. For this, for explanation, let me take a NPN transistor. Is that okay? Let me take a NPN transistor because we as assuming holes to be moving is slightly difficult. If you are okay with it, we can explain with holes, or else we can talk in terms of electrons. Which one shall I do? Should I explain using holes or should I explain using electrons? Yeah. Okay. This time we'll try it with holes only. You see, this is the base region. Try to understand this in terms of uh, try to understand this in terms of holes. If not, then I'll explain with electrons. Only the logic is the reverse. The motion is just reverse. Now, assume that there are certain holes reaching over here. There are certain holes which are reaching over here. Now, in this case, what you have done, you have made sure that there must be as less contact as possible. So, you have maintained the doping to be very less. You have maintained the doping to be very less. Okay, low doping is maintained. Now, in the given case, all this base doesn't do anything. It's just a region. So here you have a junction. This is a junction, and here also we have a junction. Its base is just a region. Here there is a junction. Here there is a junction. Let's say we are talking about PNP region. This is P. This is N. This is P. PNP region. Now listen carefully. What are these holes trying to do? They are trying to move towards emitter. They are trying to move towards this collector. Is that okay? They're trying to move towards this collector. They're trying to diffuse through this to the collector. Now why should they move towards only collector? They can move as well towards base, right? So there are very good chances that they can move towards the collector base also. So there are very good chances that they can move towards base also. Understood? So what happens is that whatever charges are reaching, so as per the priority, so few of them may go into collector and few of them may go into base. But what do we want? We want all the charges to be collected at the collector only. That means we want to tempt the charges to go to collector only. We want the charges to go to collector itself. Now, how can they get tempted? We know that current always travels along path of least resistance. Is that right? Current always travels along path of least resistance. Now, since base is doped low, so number of charge carriers per conduction is low. Since doping of base is low, the number of charge carriers available for conduction are low. Is that right? The number of charge carriers available for conduction are low. This implies conductivity is low. Is that right? That means the resistivity is high. That is, this implies base is a region high resistance, high resistivity compared to emitter or collector. Now, yes. Now, but since R is equal to rho L by A, R is equal to rho L by A, rho is proportional to length. Clear? Rho is, resistance is proportional to length. So, greater the resistance, greater the length that needs to be traveled. So, greater will be the resistance. Here, length, I can say length of the path. Length of the path traveled by the charge. Now, look here. The thing is, if base and collector were at the same distance, equal distance, then the length of the path traveled would have been equal. But in the given case, what I'm trying to do is that if I bring down the width of the base less, if I bring down the width of the base, reduce the width of the base. Now what is happening here? Now any hole reaching over here will have two options. We'll have two options. You see, this hole can cross this hole, cross this base region directly in least path, or it can travel all the way till this base. Now tell me which one it will prefer. Will it simply cross the barrier in the least distance, or will it travel all the most of the one? Okay, most of these charges, they prefer to cross, they prefer to cross the barrier, they prefer to cross the base. But the ones which are close to the ones which are close to the base, what they do? The ones, the only one, the ones which are close to the base, they only will reach the base. Understood? So majority of them will preferably cross the barrier comfortably, safely. So that's how we are tempting the charges to reach the collector, not to the base. Understood? So here what is happening? Since base is thin, the path to collector is shortest. Here, let's say very thin compared to the path base for most of the charges. Shortest means least resistance. So that's how the charges are will be reaching the collector. So here you can assume that if 100 holes are there, so out of them 98 holes will be reaching 98. Whether they may be holes or electrons, 98 of them will be reaching the collector. Two of them will be coming to the base roughly. Okay, roughly this much uh, transition. This much is the division roughly, and anything above 98 holes is only admittable. That means if you have designed a transistor in which uh, uh, there are holes less than 98% of that means 98%, less than 98% of the charge carriers are reaching the collector, then it's a bad design. Understood? In a good design, the number of charges reaching the collector must be greater than 98%. So understood the logic? Any confusion? Good. Now let's try to see the symbol for this PNP and NPN transistor. Okay, because we cannot always draw the shapes. So we have a symbol for this also. Let's try to see the symbol. Let me draw a PNP and NPN transistor, then I'll draw the symbols. So PNP, NPN, PNP, NPN. This is emitter, this is base, and this one is collector. This is emitter, this is base, and this one is collector. The thing is that what is the role of the emitter? Emitter must be emitting the electrons, or sorry, the charges. So this is the emitter current. So this will be the base current, and this will be the collector current. Is that okay? Whereas in this case of NPN transistor, you see always how to identify the direction of current means is the PN region, right? You know that in the PN region the current must be flowing from P region to N region. So here the current must be flowing from P region to N region. So current must be in this manner. So in the case of NPN transistor, only thing is that the current will be reversed. Magnitude will not change. Only the direction will be changing. So here what I can say is that the emitter current in fact if you can observe in both cases what is happening is that IE is equal to IB plus IC. IE is equal to IB plus IC. That means the emitter current is base current plus collector current. That is valid always for any transistor, whether it is NPN, PNP, any doping, any dimensions. This must happen. Is that okay? Now, how did we decide? How we can decide the direction of current? Means we have to focus on the diode. You see, here there are two diodes. We can assume, okay, in reality there are no two diodes, but you can imagine as if there are two diodes here. There is PN diode and NP diode. NP diode, PN diode. So that means PN. There are two PN diodes. Understood? In both cases, we can assume that it's nothing but a combination of two PN diodes. It's combination of two PN diodes, but in reality it's not that way. It is designed that way. Now coming to the symbol, it is represented in this manner. It need not be proportionate. This is emitter, this is base, and this is collector. This is emitter, this is base, this is collector. Now here we are talking about a PNP transistor, right? PNP transistor. So what's the major difference here? How should the current be flowing in this? The emitter current will be coming over here. From that, the base current will be leaving, as well as the collector current will be leaving. Whereas here, the base currents and collector currents will add up to give emitter current. Now, how to remember this means, you see, this is P, this is N, this is P, this is N, this is P, this is N. The thing is, we know that we have to always talk about between the emitter base junction. Now, because that is considered as the input. Okay, this terminal, this input, this is considered as input. This is considered as input, whereas this is considered as output. So in the input region, that means the PN region we have to consider. Now in this PN region, where is the current flowing? We know that current always flows from P region to N region. So this is how we put it. Here current always flows from P region to N region. So this is how we put it. Put that. Here arrow indicates, note. Arrow indicates the direction of current in base emitter or emitter base junction. It indicates the direction of current in emitter base junction. Got the logic? Any confusion? Now, if at all you people are confused, then you can remember it this way. This is a PNP transistor, right? This is a PNP transistor. This is a NPN transistor. What is happening to the arrow here? Is the arrow pointing in or out? Pointing in. So the trick to remember this is arrow must be pointing in. Pointing in. So PNP. This is nothing but PNP. Now the trick over here is that is the arrow pointing in? No. So arrow is not pointing in. So this is NPN. Okay, kindly do not laugh. These are some silly techniques to remember this. So if arrow is pointing in, that is a PNP transistor. If arrow is not pointing in, that is pointing out, that is a NPN transistor. Got the logic? So this is the circuit symbol for a transistor. Yes. You see here collector doesn't have a, you see this emitter base collector collectively it's a device. Understood? It's a transistor device. So you don't have individual applications for emitter or collector or base. So collectively, the transistor has some applications. So that applications we'll discuss once we have completely studied about this emitter. Sorry, about this transistor. Yes, the current must be always from P to N, because that's how a diode functions, right? Diode will conduct when the current, okay, it is, we say the diode is functioning properly when current is from P to N. So here, if you can see, close this part, okay, close the left part. If you ignore this left part, if you are considering this PN junction, current must be from P to N. Current must be from P to N. Then only you are operating the device properly. Now, what we have to do is that we need to talk about the biasing. Is that right? That means application of some voltage to get extract some output, so that we can study about it. So we need to do some biasing. Now, coming to this, the thing, how we can use this transistor means, first let's talk about the biasing. Just give me 2 minutes time. You see, Coming to the biasing, okay, previously we in the diode there was only two terminals, so you have biased it in okay, two ways. Okay, totally there were three ways: forward bias, reverse bias, no bias. But no bias is not a condition. Okay, so either it must be forward biased or reverse biased. So there were two cases. But now coming to a transistor, we have three terminals in a transistor. We have three terminals in a transistor. So we need to bias it. But out of which, okay, before that, I want to, before biasing, you see, there are two choices, right? In a diode, there was a single choice, P and diode. Now coming to here, you have two types of transistors. You have PNP transistor and NPN transistor. Out of these two, which one will you prefer? Out of these two, which one will you prefer? Whether you use this PNP transistor or NPN transistor? Any particular reason, Kushal? You have mistaken, Vivek. Let's see how. You see, in the given case, this emitter is supplying some charges, right? So, can I say that this emitter is supplying holes to it, the circuit, out of which some of the holes will be coming out, some of the holes will be coming out of the collector. Okay, that's the logic over here. Now, in case of a NPN transistor, what is happening? Emitter is emitting electrons. So those electrons, some of the electrons they are coming out, some of the electrons, most of the electrons they are coming out through the collector. In both cases, emission is taking place only at one point only. So here the holes they were emitted by the emitter and they were collected by the collector. Whereas in case of the NPN transistor, electrons are being emitted by the emitter and electrons are being collected by the collector. Now tell me which one will you prefer? So whatever logic you said was not appropriate. So that means input is from one place only. In both places, the input is from one place only. Now tell me, which one will you prefer? Why? Why NPN? Because the mobility, you see, now here also current is dividing, right? Kushal, NPN because current is not dividing. Current is dividing. You see, whatever current is coming, that is being divided. You see, electrons they are splitting. That means the current is also splitting. Only thing is that direction of current is opposite to the direction of electron. The major reason is that you see, conduction in PNP is taking because of holes. Conduction in NPN is because of electrons. And we know that electrons, their mobility is greater than the mobility of holes. Understood? The mobility of electrons is greater than mobility of holes. And because the uh, electrons are the ones which are responsible for conduction in NPN. So that's why I would prefer, in fact, all of us would prefer NPN transistor over a PNP transistor. Do you agree with that? Yeah, I'm not disagreeing that. You see, holes are also taking part in conduction. You see, here most of the conduction is because of the holes. There are electrons also taking part in the conduction. The minority charge carriers also taking part in conduction, but their contribution is less. Here, in both the transistors, because they are doped, number of electrons will never be equal to number of holes. That is case. That is the case only in case of intrinsic charge carriers. Sorry, intrinsic semiconductors. Here, but because here we are having extrinsic semiconductors. We have charged, we have doped them. So they'll definitely be different. Did you get the logic? Note. Here we'll make another note. Since mobility of electrons is greater than mobility of holes, and electrons are responsible for conduction in NPN transistor. So NPN transistor is preferably used, is widely used. Is widely used. Yes, that's a fact. Most of the applications we use a NPN transistor. Okay, most of the applications will be using NPN transistor, but uh, you see the direction of electrons and direction of current, it is opposite, right? So for that particular reason, what we'll be doing is that we'll be taking a PNP transistor for understanding. Okay, we'll be taking a PNP transistor for understanding the transistor. But while application will go with the NPN transistor. Only difference. What's the only difference? You see, here itself we have seen there is no variation in only difference is the direction of currents, but the relations, everything will remain same. Okay, whatever in the future also, whatever relations we are going to make, nothing will change. Only the only thing that will be changing is the direction of current. So what we'll do is that we'll conclude today's class over here. Okay, in the next class, that's on Monday. So we'll be talking about the biasing. In that, we'll see exactly what's happening inside it, just like what we have seen in case of diode or in the junction region, how it is happening and why we have connected in reverse way. Okay, why is this being the device been framed that way? We'll try to talk about it. So in next class, we'll talk about the construction of this transistor, and after that, we'll be in the other class, we'll be doing some numericals based on this transistor. Is nuclear physics done, Vivek? That means Prishti's track is done. So I'll speak to him. Okay. Maybe in 2 or 3 days, that will also be done. Uh, if you don't mind, then can you give me some extra classes? From here, I need 1, 2. So when is that possible? Tomorrow, is it okay for you people? Okay then. Tomorrow, somewhere between 9 to 12, we'll have a class. Okay, not too early, not too late. I'll inform you. Okay. Thank you.